Now let's get into the business of how do you actually generate an RSA key that works the right way. And let me be crystal clear, okay? It is not going to be obvious at all why this works, okay? When I first saw this, it took me a really long time to really understand how this works. We're going to go over this in a future lecture, but for right now, I just want you to be able to create a key. I don't care right now if you understand how it works. Okay, we'll do that later. I want you to understand it later, but right now, let's just talk about key creation. Okay, so there's going to be a lot of mystery here, and you're going to have a lot of questions about it, but that's okay. We'll answer those questions later, right? But use that curiosity to keep yourself interested and motivated. So here's how we do it. How does Alice generate her public encryption keys N and E, her modulus and her public encryption exponent, and then her private decryption exponent D? Here's what she does. Step 1, she selects two distinct primes P and Q. They should be very, very large, a couple of hundred digits each. They should be big numbers, okay? And distinct means they got to be different. You can't choose the same prime twice. You got to choose two different primes, P and Q. Then how she gets her N for her public key part is N is simply P times Q, okay? So she multiplies her two primes to get her N. Now this tells her that she can immediately compute the Euler phi function of N for the N she chose. The Euler phi function of N must be P minus 1 times Q minus 1. And the point is Alice can compute this, right? Because she knows what P and Q are, okay? Next, she chooses her encryption exponent to be a number between 1 and phi of n, whatever phi of n is calculated from right here. And she's got to choose it to be between 1 and phi of n, but she's got to choose it so that the GCD of E and phi of n is 1. So she's got to choose E so that it is relatively prime to phi of n, okay? Then that will tell her what her private decryption exponent D is. D is going to be the inverse of E mod phi of n. Okay? So then she's done. She publishes N and E as her public encryption data, and D is her private decryption key. And Alice must hide the values of P and Q and phi of n, and of course she has to hide D. Okay? So let's talk about some things that are immediately worth pointing out about this. As I said before, the primes P and Q that she chooses in the first step here must be distinct or RSA does not work. So you may not choose the same prime twice. P and Q must be different. Okay? So let's look at the second point. What's going on here? Well, because N is P times Q, the factors P and Q are necessarily relatively prime because they're different from each other. Think about taking the primes 2 and 3, right? Those are two primes and they're different from each other. What's the GCD of 2 and 3? Well, it's 1. They're relatively prime, right? Because they're different primes. So when you have two different primes, they are necessarily relatively prime. And that means since P times Q has two relatively prime factors, we can compute phi of n by what we know about the Euler phi function, right? So phi of n is phi of PQ. But because P and Q are relatively prime, that's the same thing as phi of P times phi of Q. You can break it apart. You can break this apart because P and Q are relatively prime. But remember, P is a prime, so phi of P is P minus 1, and Q is a prime, so phi of Q is Q minus 1, and that's why Alice knows her own value of phi of n, because n is factored and they're prime, so it's got to be P minus 1 multiplied by Q minus 1. Okay, continuing. When Alice chose her E to have a GCD of 1 with phi of n, notice that she is necessarily choosing E to be invertible mod phi of n. We've known this forever now, that when the GCD is 1, that this thing here, the E, must be invertible mod phi of n. And that means that D makes sense, because D is going to be the inverse of E mod phi of n. So E better be invertible for this part to make sense. So this part makes sense because Alice did the right thing in step 3. Right? She chose the GCD of E against phi of n to be 1, so this part makes sense. D as the inverse of E actually exists. That's important. Okay? The biggest mistake students make is in the fourth step. Let me point out the fourth step right here. It's right here. Okay? When you compute D, you have to compute that on your modular calculator where the modulus is phi of n, right? So you have to work mod phi of n. Okay? So that's how you compute D. You work mod phi of n, you put in E, and you ask your calculator for the inverse, and that's what D is. right? But when it comes time for you to encrypt or decrypt with Alice's key, remember all of Alice's math happens mod n. So you've got to change the modulus on your calculator back to n when it comes time to encrypt and decrypt. If you forget to do that, you're always going to get the wrong answer. Okay? And finally, it is Alice's job to conceal and hide all 4 bits of the private data, the P, the Q, the phi of n, and of course she has to hide D. All right, we're going to see later, you'll even see it on the Canvas quiz for this handout, that if Eve can discover any one of P or Q or N, she does not need all 3, she only needs one of them. If Eve can learn any one of P or Q or phi of n, that will automatically give E a way to derive Alice's private key, and that's bad. You should never be able to get the private key. Okay? Again, you're going to need to read this several times for it to sink in. Let's do an example right now with small numbers. I think small numbers are easier to handle and think about. But let me be clear. The way you generate an RSA key with larger numbers is exactly the same things I'm doing right here. Okay, let's do it. Suppose Alice chooses her primes to be 7 and 13. Notice that is okay. 7 and 13 are both primes and they're different. 7 is not 13. These are valid choices. Okay, so this tells Alice that with those choices, 7 and 13, her public modulus will be 7 times 13, which is 91. So Alice's public modulus is going to be 91. Okay? Now she's got to choose E, and there are many E's at work, and all she's got to do is pick one. There's no one right answer here. So to do that, she must first calculate phi of n. Okay? Well, that's easy. Phi of n is p minus 1 times q minus 1. But that is 6 times 12. 6 times 12 is 72. So Alice's phi of n is 72, but that's private information. Right? So now her job is to choose an E between 1 and 72, because 72 is her phi of n, such that the GCD of E and 72 is 1. I will let you check that 11 would work. There are other choices you can make, okay, but 11 would work. Okay, so 11 has a GCD of 1 versus 72, so that's a good choice. And so she will make E equals 11, the other part of her public key data. So Alice already can put out her public key data. N is 91 and E is 11. So to compute her private decryption key, she takes her E, which is 11, and she inverts it mod 72, which is her phi of n. And the inverse of 11 mod 72, you can check it on your own modular calculator, is 59. So her private decryption key is 59. And her private decryption key, of course, she has to hide from everybody. So her private key is 59, and Alice must also protect the fact that her primes are 7 and 13, and that her value of phi of n was 72. She's got to protect all of that. But that's her public key data, and this is her private key data and how she got it. And again, if you want to, why don't you take some messages between 1 and 90 and try to encrypt them with this encryption key, and then decrypt it with 59 and check that you always get back the original message, and you do. So I want you to do 3 more exercises on the Canvas quiz. Exercise 3, I just want you to do this. I make some choices for you. Trust me, these are legal choices. I choose the P, the Q, and the E for you. Simply work out Alice's private decryption key D. Okay? In exercise 4, I want you to be Eve. Okay, so pretend you're the enemy now. Alice has published her public key data, and this is all good data. N is 7363 and E is 13. You sit down and do a brute force search for prime factors of 7363, and you find that 37 is a factor of n. Use the fact that 37 is a factor of n to, unfortunately, recover Alice's private decryption key. All right? And the question is, does that scare you a little bit? Because now now Eve can get that private key from this public information. Okay, all she had to do was find a single prime factor of her public modulus. Just think about that a bit. We'll get into that later. All right, and finally, in exercise 5, you're going to be Eve again, and it's the same question as in exercise 4, but I didn't tell you the prime factors, and I claim since the modulus is 55, you can work it out. So same thing, knowing that N is 55 and E is 3, I want you to find Alice's private decryption key. And think about these exercises here when you were Eve. when we get into the discussion of why RSA is secure. By you understanding how you broke RSA in exercises 4 and 5, it'll make it clear to you later why RSA is actually secure. Of course, the punchline is going to be these moduli are way too small. You would never use a 4-digit modulus. Okay, so stay tuned for that.